So, yeah, let's start. Let's kick it off. It's really good to see you all. Yeah, my name is Andrew or Andrea. Everyone in the Anglosphere, people call me Andrew because it's generally too hard to pronounce Andrea. So I kind of years and years ago, when I moved to New Zealand, I called myself Andrew, and it makes my life easier. But I'm sure you can call me Andrea. So I'll talk about. The title is Think Twice Before Dropping Acid and Throw Your cap away. If you're not familiar with the sort of slang word dropping acid, you can Google dropping acid, see what it means. But it's actually about acid. So it's about databases. It's about the CAP theory. I'm going to talk about acid, what it actually means, some of the nuances in acid, and how some interesting things going on in the research field with database consistencies. I'll talk about the CAP, but most importantly, I'll talk about the most important thing is if you can sort of more or less forget everything I said. It's just a long intro to the final bit, which is the actionable advice for selecting your database engine thingy, your data store, however you want to call it. Because I do think there is a lot of there's a lot of ways that you can get burned by your database, basically, and I will try to help people avoid that. So, and I've developed one question, kind of like a long questionnaire list that you should go through before venturing into new land. Before going into any new project, you should try to answer as many questions as possible, and then you'll minimize your chances of actually getting seriously burned. So let's a little bit of intro about the cost of dirty data, or let me rephrase it. It's actually the cost of dirty data management, of managing the direct costs as well as trying to avoid dirty data. So you'll often hear in lots of conferences that there are direct costs, like if you do something wrong, then the government can actually close you down if you're a company in some situations, or you lose money, or the management make poor decisions because you've messed up your data. But I'm trying also, as part of this talk, I'm trying to highlight there are actually a lot of indirect costs of trying to manage or prevent dirty data. So if you know that there's some sort of data problem, and virtually every system has some sort of data quality issues, and some high-level executive asks you, well, okay, so what's the actual damage? If you have a complex underlying problem, you're not going to be able to answer that question straight away. If you have some funny consistency issues, you have to actually invest a lot of time in understanding exactly what's the damage. When you hear a lot of big companies going no SQL and having occasionally consistencies, what they actually do is they do invest quite a bit of time in actually measuring that, and that's not something that's easily done by a small team. I also wanted to highlight another thing with dirty data, which I've witnessed myself, especially on like data warehousing, and now you have data lake projects, but traditionally you have data warehouses. So what happens when people or managers or business people, when they lose confidence in data, then your data warehouse then becomes pretty useless. And then when there's enough money, people say, okay, let's just rewrite it. So even if you try to fix some of the data issues, if you have continuous issues for a long period of time, there's going to be a bad reputation. Whatever that system is, it's just going to get that bad reputation, and it's not going to go away until you rewrite it. And if you don't do it properly next time, then in 5 years, it's going to be the same story again. So let's quickly revisit ACID. What it actually means is, I'm sort of simplifying a lot of these things. Atomicity is all or nothing, doing like a batch, think your normal database commit. Consistency is integrity, think primary keys, foreign keys, any kind of constraints, null check, stuff like that. Isolation, this is the really interesting part, and this is what's actually really complicated. I'll talk a little bit about it in the further slides, but this is actually a lot more complicated than when you think it is, I'm sure. Durability is not losing data. You'd think it's quite basic, but I'm just making a little bit of fun of the old MongoDB when it was actually telling you, okay, I've written the data, but it didn't even write the data to the disk occasionally before it said yes. I've written the data. So you expect all of these in your data store, right? And even you know, unless you're really talking like some really unimportant data, you kind of expect most of the time that you're not going to lose the data. The CAP theorem, the CAP theorem says you have consistency, availability, partition tolerance, pick any two. So you can't have all three of them. You have to settle on 2 out of 3. And why was the CAP theorem actually really important back in the day? Because it sort of opened the gates towards the internet scale architectures, infrastructure architectures. So the pioneers there were Amazon and Google. Amazon was running, I'm talking databases, so Amazon was running like 100% on Oracle way back in the late sort of 90s, early noughties. It was running everything on Oracle. And they ran into some massive issues with Oracle. They had by far the biggest instance on the planet. And they had all these interesting things happening that even Oracle engineers never encountered. So it was, I tried to actually find some link nowadays. I read about them years ago and I can't find it now, but I'll try to dig out some more articles and publish them because it was an interesting read. And all of these issues led to Amazon realizing, hey, we don't actually need to use Oracle, sort of the old school architecture for most of their problems. They could actually use other databases. They could use other new engines which didn't have the consistency. So you would actually drop consistency, and then you have your availability, which is really important for making money, and partition tolerance for actually ensuring that, for having resilience as well in the system. And truly, Oracle, MySQL, DB2, sort of all of a lot of the old school RDBMSs, they don't have a massive scalability potential. They do have limits in terms of how much they scale. They can actually scale a lot. So in your world, it may actually not be an issue at all. So there's a huge difference between sort of a normal business app with a few thousand users and a sort of an internet scale app. So really keep this in your mind. It's really important that you need to know what your trade-offs are. This was the whole concept of, I'm sure you've seen this around, it's a base or eventual consistency, or the long coin word is basically available soft state or base. And this led to a lot of acid dropping, right? It was a huge eye-opener for a lot of companies that said, okay, now all these old school issues, scalability things, they were all went away. We could actually just go deploy, use big tables, use MongoDB, use a whole bunch of other tools that they allow much higher scalability. And a lot of these companies also realize there are side effects. So there's sort of dirty stuff left behind. A lot of them knew that would happen, so they were sort of prepared for it. It was a no, like, I think Amazon early on knew exactly what they were getting into. When I talked to a lot of people who sort of tried with no SQLs, they didn't know what they were getting into, unfortunately. And that's sort of I feel this is my responsibility to warn people to kind of say, make sure you know what you get into, and make sure that anyone who claims that there is no rubbish left behind, I would treat that with a bit of caution. Okay, now we're talking, just recapping on the consistency models. This is like almost straight from Wikipedia. This is my very simplified markdown of what it actually means, the isolation levels as defined by ANSI SQL. So I'm not going to talk about, if I try to explain actually what this actually means with examples, I'm going to lose another at least 20 minutes, half an hour, and it'll probably go over your head. And so you kind of have to read up on it on your own, take your time, sit down and work out exactly what it means, open up two terminals and play with the data, and then you will actually understand. And this is actually not quite, firstly, this is not quite accurate. There are even different kind of events that can happen, which there are more actually dimensions in addition to this. And it turns out that the actual consistency models, there's a lot more of them as well. So this was one of the interesting papers from 2013 where a bunch of researchers realized, so yeah, basically NSI talks about serializable, read committed, basically nothing, and repeatable reads over here. But there is actually a whole bunch of other ones. So there's a whole bunch of other, and these are all logical models, right? There's a whole bunch of logical models that could potentially be implemented. So what does it actually mean? Why should you care? I'll come back to this a bit later on. Here's a question for you. Can anyone in this room say for their latest project, latest application they own, what's the consistency model that they use if you use a relational DB? Anyone? Yeah? Repeatable read, and you use probably MySQL then? Oracle? You're wrong, because Oracle doesn't have repeatable read. Also, okay. Anyone else? Sorry? Recommitted the snapshot isolation and recommit. So SQL or Oracle? Which one? SQL. Okay, cool. I believe you. All right. So my point was actually not many people realize that what's the default that turned on. So Oracle by default, it would be read committed. You can bump it up to serializable, which is not serializable. It's actually snapshot isolation. And similarly on SQL Server, I think the default would be, I'm not actually sure with the latest version. SQL used to be a bit different. SQL was using actually locking, and he was using serializable, but with really bad locking, which was really dodgy, which could be really dodgy with locks. So the new version has MVCC, and I think the default would be read committed, or you could bump it up to snapshot isolation as well. So it's actually very similar to Oracle. And this is what you get with MVCCs. You basically get read committed or snapshot isolation. Serializable, with MySQL, the default is actually repeatable reads. But it can go up to proper serializable as well, and Postgres can also go to proper serializable. And there's lots of different, there's different database engines actually have different flavors as well. So you have to you have to test it out to really understand. Okay, second question. Does anyone in this room know what sort of, for their particular problem area, for their latest application, do you know what are the actual requirements? Like, do you know, for example, does it need to be read committed, or should it be snapshot isolation for your particular application? It depends. So sorry, yeah. So there are some use cases where you need. Okay, so I think we have one person in this room who actually knows this problem area to say, yes, my application actually needs to work in this way in some areas, and then sometimes I can relax the requirements. So, and that's a kind of a very typical, like one of maybe 50, 60 people. So it's a kind of a, my point is, yes, go look up, read it, because in some cases you may be actually you may be inserting data right now. It's maybe not a huge issue, and usually a lot of these issues are, if you don't have high volume systems, high concurrency systems, they are usually very small or nothing, or very, not significant enough. But if you have like, it really depends on the area. I mean, if you're talking about, say, for example, on one spectrum you have data which is, I would say, logging, instrumentation data, which is, who cares if you lose a bit of data if some consistency is not right. And then on the other spectrum you have financial transactions, where if you screw up even a little bit, it could be, at the end of the day, something A plus B doesn't, 2 plus 2 doesn't equal 4, and then you have a problem. And it's quite bad. So you have to, depending on your area, you should probably, try to think how critical it is for your data to make sure that 2 plus 2 always equals 4, and then read up on all the consistency data. If the more parallel concurrent activity you have, the more chances are of funny things happening as well. And question number 3, we all love microservices because you can scale up and they sort of allow a lot of goodies, but what is it when you implement if you have a bunch of REST services without any extra things, what's the actual consistency level for for your basic microservices architecture? It's actually like no acid. You don't get atomicity, you get nothing. So keep in mind that if you're implementing microservices, the big weakness by far is that when you have to do orchestration between different services and then something doesn't work, then what do, right? And this is the whole problem area that distributed transactions tried to solve back in the days, and now people kind of pretend it's not, you don't need to address it, but actually in a lot of cases you have to address it. And which brings me to the next point. There's a huge, if indeed you're using, say, microservices, and you need to handle a lot of consistency. So microservices, they all have, assuming they all have different databases, so it's all distributed. So you say, for example, you need to make sure that when you're calling two services, and you need to make sure that the two of them are in sync or almost in sync as much as you can as much as in your control. So you have to actually figure out some pretty clever ways of ensuring retries and making sure that when you get a number of errors, then you try to reverse. You have to be able to reverse one of them. You always have to basically, let's say in a payment system in PayPal, is what happens when your point of sale terminal talks to the server and doesn't get a response, right? You have to say, try to do the transaction, and then what it has to do after a while, it has to just give up and say, I'm going to assume that I didn't do transaction, but I have to then go reverse, and I can't do anything until I get a confirmation that the reversal has been done or the reversal has been received by the server. So you have to implement all of that logic, both on the server and as well on the client. So it adds a lot of, so firstly you have to think about all of this, it adds extra code. Yeah, it's not that straightforward, which is exactly why Google, this is what Google found years ago, is that they actually have a pretty difficult problem in the ad space. You have lots of bids, like real-time bids for ad space for advertisements. This is money, so it's serious when it comes to consistencies. And this was a few years ago. This was the problem statement they tried to achieve by doing the F1, which is now known as Google Spanner. And you can read about it. I'll just try to I'm not going to paraphrase it. You can sort of read word for word and see what it actually means. It just means, yes, it's if you're solving this if you're trying to solve this problem over and over again for every single application, all these different engineering teams, they're wasting so much development time, and they're probably introducing bugs that they're not afraid. So they say, let's try to solve this problem once and for all, so that the developers don't have to do that. But Google want to go one step further, and they say, yeah, let's try to do it web scale. But how do you do that without violating the CAP theorem? I'll get to it later on. So just a little bit of a joke here on NoSQL by some guy called Madsen. I found it quite funny because it's sort of what goes around comes around as well. I see a lot of, called me an old skeptic, but I've sort of been long enough in the IT industry that you see sort of new hypes, new technologies coming over, and then a whole bunch of real-world problems that were solved years ago, try to sort of get tucked under the carpet and to say, no, they don't matter anymore. Well, sometimes they do, sometimes they don't, but you should be aware of, like, even stuff like, why did hierarchical databases, why would they superseded by relational databases? Well, there is a reason, because they kind of sucked. So, relational databases solved a bunch of problems. So my point is, if you try to understand a little bit of history of where databases come along and what were the benefits, and then try to make an informed decision. The CAP Theorem, yeah, so what I said before, it was pick 2 out of 3. And I see sort of some issues. Why do I see issues with applying CAP Theorem for practical use. And this is a few times I've seen a lot of people in PayPal and other companies, they say, according to the CAP theorem, blah, 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 this is why we do such and such thing. And I'm saying, well, the CAP theorem is not a great way of actually structuring the database problem, because firstly, does it talk about the latency? No. It sort of assumes 100% availability. Is there such a thing as 100% availability? Of course not. Does it talk about the acid isolation level? Well, yes, it's actually using a linearizable isolation model. I'm not aware of any database engines who have actually implemented that theoretical linearizable model. There's a bunch of all these other implementations, not the linearizable. So it's not, my point is, it's not there are other models which you can get away with. It's also not using, this is a little bit of a side mention, it's actually all based on, like, what about some other kind of, shared disk storage or InfiniBand clusters, some kind of more specialized hardware? No. The CAP theorem is only about commodity hardware. So, there could be other ways of solving the problems. Not that I'm advocating for any special hardware, but just keep that in mind. And this is one of the other key points, is that the CAP was based on linearizable, and then other people also figured out that basically the CAP applies to all of these red ones here. And then you can still get away with, so that you can still get, in theory, you can still get away with your, say, read-committed isolation model and be available and be partition tolerant, right? So this is quite I'm sure that people from Google realize that and say, hey, we can be read-committed, which is kind of okay in some cases, and still achieve all of this and still get the goodies. And this is how this is one of the keys, this is one of the main reasons how they managed to pull it off. So you can call it sort of capital, like lowercase CAP and not capital CAP, but it still kind of works. So now this is I'm going to go through this because this is really, really sort of important. This was all I talked before. This was just like a very long intro. This is kind of some useful stuff here. So when you go and try to select your database, or try to educate yourself on how to select the databases, I try to come up with as many points of questions you need to understand in your head before, or try to make educated guesses before you can actually make a good choice. So ACID is, so firstly you start with, say, ACID, do you need atomicity? Do you have cases where you need to commit multiple operations in a batch? How I'm going to handle data referential integrity? So you could throw away all the foreign keys, unique keys, and then try to figure out some other way. Well, actually, primary keys you can't. Let's say for foreign keys you can actually get away with if you're doing a lot of testing to make sure that you're not messing up any data, or you could try to do post-hoc testing. Again, all of this stuff adds onto your, if you have a foreign key constraint, you know for 100% sure you're never going to get bad data. If you don't have it, then you need to invest into additional measures of trying to detect it and prevent it. What isolation level do I need? So you have to sort of read up on all the stuff I was talking about before, trying to understand the problem area. Am I okay with losing any data? So yes, in some cases maybe you're okay, right? So you need to ask yourself the question, can I lose the data? If you say, no, I can't lose any data for legal or some very other good reasons, then you have to, you may discard a whole bunch of options you have. Availability, latency requirements. This is not just database, but in general, sort of microservices can, in some situations, they can, the way you design them, they can add to the latency, and especially if you're doing a lot of synchronous calls, and if you're not trying to optimize by using asynchronous calls, then the whole, the latencies can blow up, and then if the latency blow up, that basically can be quite bad for overall. Your system can be available, but if it's taking 6 seconds for for your system to respond, it could be interpreted by end users as basically it's too slow or unavailable. Performance and scalability. So this is one of the key reasons why you would want to go with some of the new products, right? If you don't have very strong scalability requirements, I would kind of suggest, my gut feeling would say, okay, you probably want to stick with something which is, proven and you get all the other benefits. I don't really see, for a lot of basic stuff, I don't see the point of selecting some fancy new database that you don't know about enough and that's super scalable and you don't actually need to be super scalable. So the key, one of the really important things in selecting the database is to go through all of the different performance workloads, the kind of, and this is very sort of, I'm talking very sort of specific database kind of things. You need to understand what kind of system it is. Generally, you have OLTP systems and OLAP systems, and they have very different things, very different operations. OLTP is lots of like parallel operations, very small operations, either reading or updating data. OLAP, you have lots of bigger reads, and you have different kind of less use of index, and you have sometimes hash joins and a whole bunch of other things that you need to have from your database to make it work well. Who sort of understands most of these? Anyone in the room? Yeah, cool. So you must be sort of database guys, right? Yeah. So in some, you do. I mean, this is why it's good to have like even if you have a development team, you want to have someone with database knowledge that can actually try to steer you towards, or try to at least discard some of the options that you don't need to have. This is a very important thing for developers, is to understand flexibility and the evolution of the database schema. So when you start, you think, oh, it can be quite easy and tempting to go, no SQL, I'm just going to put some JSONs in, and it's really easy, I don't need any ORM mappers. But then what happens when your schema evolves, and it starts evolving more and more and more, then you have to basically implement the whole database management thing yourself, or you get some, I think there are some sort of additional products trying to manage that for you, but it just becomes very, very messy and sort of clumsy. And my point is, no, there is no such thing as a schemaless database. There is always a schema if you have a database. The question is how you manage it, or do you kind of manage it within, do you have to write your own code to manage it? Do you let the off-the-shelf product manage it for you? Do you need, there's also some other very important when it comes to flexibility is, if you have like very simple reads and writes into tables, then it's kind of easy to just do like a simple product will do the job. If you have lots of different, if you have more complicated joins, more complicated queries, then what the database engine provides for you, it actually does a lot for you. I'm talking about the old school database engines. It actually keeps statistics on all the different tables. It knows what kind of available options it is. It's the optimizers are pretty sophisticated after like 15, 20 years. It can, and it'll do a lot of work for you. If you have a relatively simple engine, and you can also do a lot of optimizations, but a lot of the time you have to do that manually for every single query, right? So it's not impossible to do it in some of the newer products, but it will just take a lot more time and a lot more knowledge. Most of the time, after 15 years of evolution with the modern database thing, you can just throw in a query, and it will actually get the best. Like in 99%, it will actually get the optimal execution plan. So data recovery and the resilience. So again, mature products here, they have the ability to, when something goes wrong, when something seriously goes wrong, right? Maybe your hardware failure plan that you planned for failure and everything, something went terribly wrong. All your servers have crashed, or hard drives, or some viruses get taken over and just starting to write stupid data to your database. There can be once in a blue moon scenarios where you actually need to restore your data, and I'm sure the database guys will know it happens once. You try to avoid it as possible, but when that thing happens, you need to be able to restore point in time. So that's one of the requirements for the database engine to be able to do that. The database engines that have good consistency, high consistency levels, it's actually very easy for them to move back and forward in time. The ones in don't, it's actually, you might be able to, you might figure out you have to actually do a lot of stuff manually. So yeah, you kind of take a snapshot back and then you go through the logs and apply a whole bunch of manual operations trying to figure out how to actually reconcile the data. It's very ugly and messy and inexact science. Standards. So if I decide to move to another DBMS later on, am I prepared to invest a lot of effort into rewriting the data layers? So of course, SQL, one of the main points of SQL is trying to establish a standard. So if you want to go to another product, it's pretty easy. Nowadays you have Hibernate or NHibernate or data framework in entity framework in .NET, where it's actually quite easy to you don't have to worry too much about the data access layer in your application. You do have you still have issues. Migrating the database is not a it's not a simple task. If you're in production, if you're pre-production, you're still sort of developing the code, then it's pretty easy. But if you're in production, it's still not a simple exercise. And there's a whole bunch of sort of TCO. I'm calling TCO risk things. This is kind of like, okay, I want to use one of these new products, but I'm not too familiar with it. But I really think, or maybe one of the old products is just not doing it. I really think this new products might be able to do it for me, but I'm not sure. So you kind of have to ask yourself, what's your risk appetite? How are you gonna manage that during your project before you go live or after you go live? How do you manage that risk of the unknowns? What are all the unknowns? Are you okay to get late night phone calls? Is this application critical? Like if you work for a larger company and you have 50, 100 different applications, then obviously you want to migrate first with the low-risk applications. You can only do so much testing with testing. Sometimes you need to let things run in production, and then only then you will actually figure out what your product actually does. And of course, then you want to select the low criticality products. And yeah, there is also a lot to do with, if you have complicated queries, then monitoring instrumentation becomes really important. Again, with very stable, mature products, you get a lot of instrumentation because these are things built up over time. With some of the newer products, I'm sure that a lot of companies like Google would have used some of the old school knowledge to try to build a similar kind of level of instrumentation. But in some cases, I'm sure that if you have just a bunch of developers writing open source products without a lot of experience, then they're not going to put in all the actual instrumentation required to figure out what's going on when something actually goes wrong, or when you hit performance issues or any kind of other funny issues. Alerts as well, like having actually, so the way, if you're talking DevOps, everyone is kind of talking DevOps now, meaning developers need to be involved in operational support. And when something goes wrong, minutes can actually make a difference. How do you know when something is going wrong? Is you need to have alerts. If your alerts are if you're not alerting enough, then your basically critical time is wasted. If you have too many alerts, what happens? People start ignoring alerts, and then you get nothing. So you need to kind of, alerting is actually quite hard to get a sweet spot of, I want to really alert things when things are going really wrong, but defining that wrong can be quite complicated. My point is a lot of old school databases got some, over time they know heuristics, they've sort of, just by experience, they know what sort of good alerts, what common sense alerts are. So that's something that you want to, when you're going out, venturing out to a new product, maybe there could be some learning period for that too. Existing APM tools, in the old time, it was every product had its own kind of monitoring APM system. Nowadays, people are trying to consolidate. So the question for the vendor is does your database support some of the APM things that you already have? And then you also have to think maybe about security, right? So like basic stuff, of course, I'm just talking basic security, username, passwords, of course, everyone has that. almost everyone, but it gets actually higher than that, right? You have, say, for example, you have PCI DSS. Do you need to, so there's different ways that more mature products can, the different levels of support. The basic one is just like transparent encryption, so it's all still software-based encryption, but you can still tick the box in the PCI stuff. The next level is actually integration with, seamless integration with like hardware, HSMs, hardware secure modules. Yeah, and so there's, you know, you do get benefits if you're into some of the high security space. There are definitely benefits of the mature products, which have covered that. And also there is I highlighted that, there's multi-tenancy support. That one is probably, to me, that one is a kind of a, maybe interesting thing to have, depending on how you're actually managing the whole database database deployments. I reckon nowadays with, you know, you have a lot of, I don't think, I'm not actually an expert is Kubernetes, but I don't think that production databases are still quite the right fit. I think Kubernetes probably needs to build some more additional things so that you can manage databases in such a way because of the dependency on data. But anyway, there's, in some cases, multi-tenancy support could be actually helpful, and some products do support it. A little bit of a side note, a lot of these things are just your sort of, this is not rocket science. This is like I looked at non-functional requirements, I looked at my experience, and I thought, okay, make sure that you cover all the lists from non-functionals. So it's, you know, this is sort of still pretty back to basics kind of software thinking. And then some questions. So when you go to the, say for example, you want to experiment some new databases or products, and you want to, you find a vendor, you talk to the vendor. So how do you structure that conversation? So firstly, you want to come up with all of the lists you have, go through that list, and then understand, try to dig as deep as you can. And then say you have one of these systems, then you can actually ask them, how does your solution perform under some unusual scenarios, right? And the unusual scenarios are typically, so the hardest things for a database engine to do is to do everything it's supposed to do when there's something serious going on, like resharding, repetitioning. So say one of your server go down, or more than one of your server goes down. So the database needs to handle all of this stuff in the background and magically somehow, right? It's actually really hard. One of the old slides you've seen, a company called Jepsen.io. So what they do is they specialize in testing. They've built actually an open source suite which does a whole bunch of tests on the database and trying to basically break it. It's a very black box testing, but it's very sort of sophisticated, trying to break it, and then basically they have to turn off, and basically they try to shut down servers, effectively throwing a chaos monkey during a bunch of tests and trying to actually figure out what's going on. And the way they do it, they say every single test they do, it has to be, they have to publicly release it. So you'll see a bunch of, they tested MongoDB, VaultDB, they've even tested Kafka and a whole bunch of other products. And virtually I think none of them lived up 100% to their claims. And what happens afterwards is the vendors go and try to actually fix these issues. But, you know, that's sort of just looking at that should open your eyes to the fact that this is pretty serious. You know, if you're talking very high scalability, availability, and everything, it's actually really hard to do. And if your vendor tells you 100%, then you should probably be quite skeptical. It should be it would be a lot more convincing if they told you, in some cases, this is, you know, if you get a lot more nuanced response. You should also, you can always ask them to show you the money, which means, how do you, if their claims are, in practice, if they don't prove it, how do you structure, how do they get penalized for not being quite 100% across their actual products? There's always, if you have a good partnership with your vendor, it should be like shared revenue, shared risk, or shared, should be some sort of you can try to find levers to actually, put in some consequences for the product not performing to its KPIs, or at least you can ask for, show me the evidence. So you can open them up and say, show me the evidence of all these sort of any independent third parties companies doing all these very extensive tests. Otherwise, you're basically left on your own to try to prove or disprove that their product is working up to the expectations. And also to consider is, the final thing is, so rather than having one DBMS, then can you try to split up? Can you try to, so you look at all the performance workload requirements, and if they're quite different, if there's lots of different things, then you try to find very creative ways of mixing A plus B. For example, you could mix Cassandra and Apache Spark, and in some cases, actually, they could be quite okay. So Apache Spark is good for OLAP operations. Cassandra is quite okay for OLTP, and then you build a bit of a bridge between them, or you take a bit of open source code and it does it. So there's lots of more, nowadays, my point is there's a lot more combinations than just one DBMS. You can try to do some mix and match. Of course, that's gonna increase the level of complexity you need to carry in your head, which is, again, it's something you have to be aware of. You have to learn then not just one, but two products and a bit of integration, and it may make your life more difficult. And for open source solutions, I mean, they're great because they are free, but what happens if you need to have someone on call 24/7 and you need to get response call within minutes, and so all that sort of, and what happens if, how do you actually structure the whole resolution if they don't actually, if they're not in control of the products, and the whole resolution time, ownership of the actual, a third-party consultancy can't guarantee that the product is such and such. They're not necessarily in control of the product itself. They can provide support, but not necessarily guarantees for the exact behavior. So there's, there are, if you have, in a lot of cases, it's still easier. It's a lazy approach, but it's actually easier to pay more money, go back to one vendor, you hold them accountable for everything, support and everything, and then basically they can get stuff done. So that's basically it. What I do, I just sort of splashed one page. If you really do have a high scalability problem, there's a few names. I'm not going to endorse any of them. You have to do all your research yourself. I just literally played around with a few of them. I don't have too much time right now. My day role is basically building, helping teams build apps. Not really, unfortunately, I'm not in the infrastructure team at PayPal, but this is something, if you want to really go to the next step and go deeper into NewSQL, this is a reasonable start. I'm sure there's going to be more players, and I'm pretty sure that in one way the old Oracle, Microsoft, the old vendors, some of those RDBMSs have sort of peaked, and they're not going to go away for sure. There's still a lot of use, and a lot of companies who are risk averse, including PayPal as well, they'll still keep using the old products, but at the same time, without major re-architecturing based on all the latest research, I think they will slowly decline to some level. So I think a lot of these new databases will actually pick up, as professionals, I think, and if you're into databases, I think in 5 years you'll see a lot more of them than you see now. So you should probably start, getting your hands dirty and investigating. So yeah, and definitely read up more about consistency models. I think that's really important, not just for DBAs. It's really important for developers to understand that. It's not a DBA only task. It's really, you can say it's a backend developer. Any Java.NET developers should understand. You can start playing with new SQL if you really want to, and share the pains, the questions. It's really. I've always tried to ask different people from different companies about the pains they have, and people got burned with databases, not just no SQLs, with other databases as well. So there's always, databases are quite a tricky things. This is why I got into them into the first place. A little bit of a just final closing remark is that anyone who says, some people say, you have to go eventual consistency, or you have to go this, or you have to go that. Well, That kind of, to me, that really doesn't make sense. You have to look at your problem area, what you need to, what the basic essential complexity is that you need to do, and then you work out from that. Anyone who's saying you have to go eventual consistency, to me, it sounds like some sort of a sales pitch, right? And that's it. And questions.
Any questions? No, wait, you're recording this. You need to send the question to the mic.
Do you prefer any other model to entity relationship, or in your talk? Basically a bunch of your problems are consequence of entity relationship model. So
entity relationship model, right?
Yeah.
Okay.
So do you have opinion on some other models or something like that?
Look, hierarchical models are actually busted, right? So I'm kind of, because firstly, hierarchical, this is a little bit of a different talk, right? But the hierarchical data model is real busted. It doesn't work, right? So you have any kind of XML kind of like structure where you have strict hierarchies. In reality, unless you have some very simple, unless you have very simple data, it just breaks down and it becomes a nightmare. There is a different, relational is the old de facto standard. The only one new model which comes to mind, and it's not really actually a database model, it's more of a engine, the way it works, is the graph. So you have Neo4j and graphs. They are interesting for a different reason, is that graphs are really good for some kind of operations, for shortest path search, for kind of GIS searches, for relationship things. But you also have to bear in mind, so this is the key thing, the relational model is a logical model of the data. The relational model was designed so that you have a pure logical model, and then the database takes care of the implementation. So the relational model is not row-based or column-based or anything like that. So people get there's a lot of confusion, like what is relational model, what is this? This one is probably worth enough talk on its own to try to say this is what it actually means, this is what it does mean. So there's the relational, you can talk about, I usually try to say the current relational databases, and I mean usually Oracle, MySQL, SQL Server, that kind of stuff. They're not 100% purely relational, by the way. They don't implement the relational theory, which is the basis of the relational model. They don't implement it 100%. And how they implement it, whether it's row-based, column-based, this or that, it's actually that's not a relational model question. Relational model is about how you logically model the data. So I'm sorry, I'm not being very clear, but it's not a, definitely. The relational logical model is by far, it's the best model, it's the cleanest model, because you only implement the model, you only design that logical model once, and there's basically most of the time there's only one way to do it right. What can happen in reality is that you start trading off to say, here's my pure logical model, and my database does not allow me to have that level of abstraction between the logical and the physical model, and hence I'm going to start bastardizing when I create the tables, I'm going to do denormalization and all of this, and I'm going to manage that by bastardization the best way I can. Okay? This is the way I kind of look at things. So the logical model is still relational. What you do in the background is you're managing that sort of disconnect between the pure logical model and the actual implementation. Ideally, the database engines should do all of that, so that you're just focusing on the logical module, which is the pure domain problem, and you're not focusing on the implementation. In practice, yeah, it's I think no databases today are purely relational. And even like when they're saying graph model, you can still model exactly the same thing in a logical way and have the database implement so the implementation of graph like Neo4j could still have like a SQL-like interface, or a better version of basically a SQL so logically it's still a relational model, but the way it works, it uses graphs and and the graph theory to implement it.
Anybody else? Okay. Thank you, Andrea.
Oh, thank you. Thanks a lot, guys.